have quite a bit of experience in proving properties of logical systems nowadays, right? We normally kind of start with a system either of sequent calculus or natural deduction, and we try to prove the obvious results, meaning we want to prove cut elimination if it's a sequent calculus, we want to prove normalization if it's a natural deduction, we want to prove substitution works, we want to prove alpha conversion, which also subject reduction, which was one of the important ones for Brigitte yesterday. So we know what is that we need to do. And the question is, can we do it, and how easy it is to do it? And much to my surprise, when we kind of try to look, because as I said, these systems have been proved to satisfy cut elimination in 1957, so quite a long way away. But when we try to show that a system of natural deduction that looked like that for the rule of introduction of box to the right, we discovered that that does not work. And that was a big surprise for everyone concerned. So we kind of tried to tell Abramsky that the proof that he had was not working, but it's still there. And the system does not satisfy substitution. And I'll show you in the next slide a very simple example to show that the system does not satisfy substitution. But I think before that I wanted to mention that, that Phil Wadler, because he was trying to program this stuff, was the first one to notice. And he came up with this very double-edged title, because he kind of came up with this paper called "There's No Substitute for Linear Logic." And yeah, so people thought they were saying, oh, it's so good, there's nothing better, right? But he's also saying that the substitution was not working, meaning the substitution, right, meaning the syntax and the semantics. Because the point is that, for me at least, one of the big things to see is that the category theory playing a role was that we kind of managed to solve the problem by using category theory to see what the system should look like. So let's look at the example. I was saying this rule is global, not local, right? So, assuming that you have a proof of, you have a proof that you have an A1, box A1 and box A2, and that gives you a B, and then this is a perfectly decent proof, so you can put a box B, because everything is boxed on the assumptions. And you also have a perfectly decent proof that is a little bit more complicated, because it says, it's actually simpler, right? Because it's just more exponents. You have C proves box A1, and C, so you have box A1. Now, you don't even think about it, right? But proofs have to be substituted into other proofs. The trees have to compose. So you can try to put this tree on top of this A1 here. And what happened? It's a problem, right? Because when you put the A1, you substitute the box A1 by C arrows box A1 and C. These guys here do not have the proper shape anymore. They are not boxed. So this whole thing is not a proof. It stopped being a proof. And that, guys, is a problem. It's a problem that's still kind of bugging people kind of nowadays when they are doing cubical type theory. So there's a thesis from 2023 saying, yeah, modal logic is a problem. We have to deal with this sort of issues. And okay, by now we have a collection of ways of dealing with the issue. But when it first appeared, it was very surprising, because everyone thought that the problems would be on the normalization issue. But the problem is long before normalization. It's on kind of just composing trees. So, how can we solve this issue? Well, there are several ways of solving it. The ones that we came up, just when Phil came up with there's no substitute, is to say, oh, okay, let's kind of, we discussed yesterday that the important rule in Lambda-Calculus is the abstraction rule, the one that if you have an A and you have a proof pi and you prove a B, then you can introduce an A implies B and you discharge the A. But in normal logic, because you can have the assumptions repeated over and over as many times as you want, you can have the A present or not present. It's all right to have a vacuous abstraction. Now in linear logic, it's not okay to have a vacuous abstraction, and in modal logic, it's not okay to have an introduction when the context does not have the correct shape. So the way to do that, one of the possible ways of doing that is actually kind of forcing the rule, the introduction rule, to discharge all the box things in one go. So you get a rule like this, which is clearly not a local rule anymore. You have to kind of know all the things that are going to be substituted. And you can do this rule, and you can create terms for this rule. It's another one of the things that even for normal propositional logic you can do is use lets, right? Let X be something into something else. Oops. And lets and you can eliminate lets by a more complicated version of case. So we normally don't do that for intuitionistic propositional logic because you can do it much easier with projections. But some logicians prefer to use lets and a kind of case, the destructor for let that comes with the let, and that can be used to solve this issue. But then you end up with lots of something that people in functional programming don't like to deal with, which is the so-called commuting conversions. So it's not very pretty, kind of when you have to deal with these extra rules. They multiply again quite a lot. There's a different solution, which is a private solution, which is to invent a notion of essentially modal subformula that also guarantees the substitutivity, and that's very old, it's 1965. But that one is also very bad for implementations, and it's hard to get right. In his book, Pravitz has to do 3 different systems to get to one that works. So there are several improvements, and these 2 solutions, Pravitz in 1965 and ours in 1993, are not enough. But I thought I was going to show the rules as we have with the intuitionistic ones. Now they're becoming as complicated as Anya's rules, as you can. You have to think about all the hypotheses that you're dealing with. Now, this system is very well behaved. You have axioms that satisfy the deduction theorem. The axioms are equivalent to sequence. The sequence from 1957. The sequence satisfies the cut elimination and has subformula property. The natural deduction in the new horrible shape rule is also equivalent to the sequence and the axioms and satisfies normalization and assigns lambda terms that are Curry-Howard equivalent, and that's all readable. And I put in the GitHub that I gave you guys with papers, there is one that does all the calculations because they are pain in the neck but need to be done. So you have lambda terms that are really equivalent to the sequence and to the axioms. And you have a categorical model, which is something that, you need a CCC to model your intuitionistic basis, because, the basis is just intuitionistic propositional logic, so something that we know and have known since the 60s that corresponds to a Cartesian closed category. And on top of this Cartesian closed category, you need to have a monoidal comonad. And this monoidal comonad has to satisfy box-strong. It has to have also this monad for the diamond, and this the relationship between the two, which I discussed at the beginning, have to be that the monad is box-strong. It's all kind of a little bit hairy. And, you might think, if you are more of a mathematician, you might think, oh, that's everything I want for a Curry Howard. I'm good. Well, kind of good. Not really good, really. There is some issue with the Paiva's formulation because the way of thinking of essential modal formula insists that the comonad has to be idempotent. And that means that the box A is equivalent to the box A. And if you're just thinking of logic, you don't care, because it's just true that box A proves box A. It's one of our axioms. And it's true that the box A proves box A, so they are equiprovable. But when you're doing categorical proof theory, as I was kind of trying to talk to you about yesterday, you don't want anything that's equiprovable to be isomorphic. You want to keep the different proofs apart. And the proofs that go, and whenever you have a proof that goes from some A into a B, and then you get another proof that goes from B to the A, you only want to say that they are equivalent if the two compositions give you identity in each bit. And that's something that Anna is going to talk lots later, because it's about identities in the types, how the types should be, what can we say about identities on the types. So, in principle, we don't want our comonads, our box operators, to be idempotent. And as I say, then the philosophical logicians come around saying, eek, this is horrible, impurity of the rules. The rules are not pure enough. They are not about, if you remember, let's look back to this is ugly because of the building up all the substitutions. But even this is ugly enough because, as I was mentioning yesterday, this one introduces the box on the right, but assumes that you know it already on the left. And this one is even worse because to introduce it as an assumption, you need to know what box actually means. So that's what the philosophical logicians called impurity of the rules. So it has some good things, but it has some very bad things. So the philosophical logicians don't like the impurity of the rules. The functional programmers detest the commuting conversions. And the mathematician looks and says, and what about other model logics? Okay, CS4 is not brilliant, but at least we can do it with these difficulties. But can we do the rest? And, all the calculations are done in this paper because some people are better at calculations than others, and Gavin Bierman is much better than I am. Now, one of the things that people then discovered was that we could change the syntax and keep the semantics. So one of the good ways of changing the syntax is this thing that Frank Fanning came up with and a student of Gordon Plotkin came up more or less independently. And I'm citing Andrew Barber, the student, because he actually proved everything with the dots. Frank is not very keen on the category theory, so he couldn't care less. But Andrew did. since he was a student of Plotkin. He kind of came up with a system where instead of having formally and kind of saying that some of them have a box and some of them have a diamond and some of them have nothing at the starter, we separate things. So we have this division in the context, and on one side of the division we have things that are naturally boxed, and the other side is the things that are not boxed. And with this trick, you always have to pay the price. You always have to do more syntax. But so part of the syntax is that you have modal variables and intuitionistic variables, and you have to have the rule that Anya kind of described about introduction of variables. You have to duplicate them, right? But and then the difficult rule that I had before, the promotion rule, kind of gets a little bit easier to deal with, because the only thing you have to say is that there's nothing that doesn't have a box in front of it. So this is the empty here that makes a huge difference. And with that, you still do some commuting conversions. So, life is not perfect, but it's much better. So you have less impurity on the rules, less commuting conversions. But what about diamonds? And what about other modal systems? So the search goes on. Now, there's another system that's also very well behaved, and it's called lax logic. And that one comes about in a fun way, because this started life not as a logic considered by logicians, but a type theory considered by computer scientists. In this case, Eugene Moji, who came up with this thing called the computational Lambda-Calculus. And I also mentioned it vaguely yesterday, because the computational Lambda-Calculus kind of says that some terms are values and some terms are computations. And you know what? It's this kind of a very, Eugene used it for a meta-language for the notation semantics. And with that, he could, and lots of other people have since then, model things like non-termination of programs, different evaluation strategies, non-determinism, all sorts of side effects. So this notion of a monad, independent from box and diamonds, this is also very useful for us. But then you can use the Curry-Howard backwards, because it is a type theory, it's a well-behaved type theory, so you just forget the terms and you get a logic that had been considered by Curry in 1952. So the reason for me to be telling you about how this goes is to show that, I might be a dreamer wanting Curry-Howard to go to too many things. But there were some kind of good indications, right? This one, no one kind of could come see it coming either, because Curry considered this modal logic in 1952, and like most people, he said, "Oh, this is crap. This does not work because it has some unwanted properties as a logic." But the properties are very wanted when you're modeling programs, particularly when you're doing the notational semantics and trying to deal with things like exceptions, non-termination, non-determinism. This logic works very well for these things. And the lax modality axioms are something like, if something is valid, then it's possibly valid. If something is possibly valid, then it's possibly valid. But so these two are very much like possibility axioms, but the third one is a necessity sort of axiom. So it looks like a box instead of looking like a diamond. So it's a hybrid, a slightly schizophrenic modality that has this name, lax logic. And it's been useful for lots of interesting things like hardware constraints. Would you believe it? And you can read about that too in several papers. So it's also called CL logic for computational lambda calculus. It is Curry-Howard equivalent to a strong monad on a CCC. It makes this semantic distinction between computations and values. And it models values of a type. So T of A is the object that models computations of the type A, and the type A is just values themselves. So it's a curious possibility-like modality. And you can read, and it's very old, you can read it in 1997. Now, I want to go back to the problem that I was saying to you a little bit early on, that, I had a hope that we could do loads of different modal logics. And, and I wanted them satisfying all the things that we're talking about here. So action, sequence, and natural deduction always proved equivalent. Deduction theorem holding. Substitution and subject reduction properties holding. The term calculus strongly normalizing. Reduction systems confluent, cut elimination. And this all holds for lax logic and holds for CS4. But for very few other things. In particular, the main system that the logicians kind of like to think about, which is the case system, the very basic system of modality, it doesn't have all these properties. And one of the choices as a designer of type theories that you have to make is whether you want your possibility to distribute over disjunction or not. And if you kind of think that, and the philosophical logicians like this property. They do think that if A or B is possible, then either A is possible or B is possible. And they also like the null reversion, which is that if something is possibly false, then it's false. Some of the people who kind of invented logics invented type theories for programming don't like those things very much. So Anilne wrote, that I showed a picture yesterday, was the first one saying, for my calculations, neither of these two work. And he kind of was the first guy proposing that we ditch these axioms. And from then on, there's been lots of different desiderata for logical systems and type theories with modalities. So I've forgotten to mention that that the dual context formulation works best for the box fragment. There are attempts at doing the diamond, but they're not as good. The cryptic semantics is okay for everyone. We can do cryptic semantics for everything. And I don't know of a syntax for CK style diamonds, as I mentioned yesterday. There's something disturbing about the non-uniformity of the systems. And to me, it looks that much more work is necessary here. And I'm happy to hear that lots of people are starting to think about that. Some of them, because they are thinking about cyclic logics and cyclic type systems, recursion and stuff like that can be dealt with using cycles and loops and stuff. But before we kind of go to the things that are happening right now, I should mention what the alternatives that I know of, and their old ones are. So the main alternative is Simpson Systems, family of systems that he produced in 1994. And this is pretty good. Lots of people did lots of work on that, and Simpson's thesis is a brilliant piece of work. It's worth looking at it. So he has a very robust system, which not only does intuitionistic modal logic, but has geometric theories over it. And his main justification for the systems that he produced is that there is a translation of the constructive modal logic that he has, which nowadays are called the systems IK, into intuitionistic first order. So he recovers most of the systems in the literature. It does satisfy, some of them systems satisfy strong normalization and conference. Well, I say for all systems, so it's just that normalization here is a little different. And it does prove completeness of the cut-free sequence. But decidability is not totally guaranteed. Very recently, LIX 2024, there was a proof of decidability for IS4, but in the website of one of the authors, there is still some caveat saying that we're checking determination. Some other people tried, but it is the main alternative to the systems that I was talking about, are the systems from Simpson, from Alex Simpson. For me, the problem with the systems is that they don't have categorical models, which is a bummer. There are other systems that, again, lots of modal logicians are not interested in categorical models, so if they have cryptic semantics, they are fine. So Arnon Avram has a system on hypersequence, which is based on much earlier work. Simone Martini, Andrea Massini have a two-sequence. Dozen has some higher order sequence. Sure, sorry, I didn't see before. Sorry.
This is about a few slides ago, I guess. So you talked about three things. You said Lax Logic, CS4, and or CL and CK were early promising initiatives. I think I'm missing what about the last slide for each of those systems lists a bunch of things of desiderata that they satisfy.
Yes.
I'm missing what is the key thing that each of those does not do that renders, so is it like they don't accomplish the vision you had 20 years ago for some reason, or is it like there is something in common to all of them that makes them fundamentally unsuitable to accomplish that vision despite the fact that they were promising at first?
Whatever is fundamental is very difficult to
in your opinion,
right? But I think for me, a logic is worth being called a logic if you can provide actions, natural deduction, and sequence, and prove them equivalent. If you don't have the three of these kinds of systems and show equivalent, your logic is defective in some ways. I think this idea of only having axioms by themselves, even if you do prove sound completeness, is not good enough, because the properties of the proof theory are the things that make the systems implementable and usable as reasoning systems. Now, that's not the whole answer, right? Because what you call axioms, what you call natural deduction, what you call sequence are up for dispute, up for discussion. And I will kind of carry on a few more slides talking about the desiderata of each one of these people. I haven't talked about, I've only talked so far about my own desiderata, but I want to show what other people think is the desirable characteristics of a system. Hang on a minute. Right. We're good. And as I say, I just want to mention that there's much more recent alternatives that I haven't kind of worked very well on them. And these are much more from the type theoretical perspective, kind of starting from the type theory, and not paying much attention to possibilities. So, as I just said to her, what I wanted was constructive model logics of axiom, sequence, and natural definition proved equivalent, cut elimination, finite model properties, strong, if possible, normalization, confluence, and decidability. I also wanted different kinds of models. I wanted algebraic, crypt, and categorical semantics for every system, because, having different models for the same logical system shows that you understand the system better. You have different ways of looking at the system. And the other thing I wanted is this business of translating proofs more than simply translating theorems. We don't want to think, I never want to think about simply whether some formula is a true theorem or not. I want to think about what are the proofs of this particular formula from these particular assumptions. So this is something that most logicians nowadays think, that you should think about. They think that you should think about consequence relations. And I kind of want to have named consequence relations, so different proofs themselves. So I want a broader view of constructivity or modality. And if possible, I want limitative results, meaning I want to see when something is not possible. So, that's why your question so resonates with me. I want to know when something is not possible, if I can. Now, Simpson had a different sort of desiderata. So the things that he thinks are important are that whatever intuitionistic model logic is, it should be a conservative extension of intuitionistic propositional logic, which we agree with. He also thinks that it should contain all substitution instances of theorems of IPL, and it should be closed under modus ponens. Okay? We are good. We also agree on that. Now, he does think that a disjunction property is an essential part of a constructive model logic. So if A or B is a theorem of putative intuitionistic model logic, either A is a theorem or B is a theorem. Disjunction property is essential for him. And he does want box to be independent from diamond, which I do too. But here we get to the crux of the difference, because he thinks that when you add the excluded middle to your intuitionistic model logic, this should yield the standard classical model logic that you started from. And here's philosophical, right? Because you might think